Great. Hi, everyone. Thanks for tuning into the weekly Quantum Chaos seminar. It's my great pleasure to introduce today's speaker, Juan Diego Urbina, from the University of Regensburg, where he's currently an assistant professor. So Juan did his PhD thesis at the Max Planck Institute at Dresden, before continuing on to do a postdoc at both the National University of Columbia and the Weizmann Institute of Science. So he's worked on a variety of topics, and today he'll be talking about universal signatures of many-body chaos and integrability, semiclassical theory of quantum interference in Fock space. All yours, Juan.
Okay. First of all, thanks, Paulo. Thanks, Peter, for the invitation. Great that you put together these talks. I enjoy very much two of the last talks. I have the pleasure to watch, and welcome everyone to my talk. So I will be telling you essentially about how to take the idea of interfering patterns, semiclassics, from single particle to Fock space today. So I want to present part of the collaborators. Joseph was in Regensburg doing the out-of-stand order correlators I will show. Benny is doing integral many-body systems. Klaus is our boss. And I have the pleasure to collaborate with Steve Tonsovic in Washington, Daniel Mo in Orsay, and Peter Strakek in Liège. And I will show you very important work made by Thomas Engel at the time in Dijon. So I don't want to go into semantics here, but just to set the stage. Well, what do I mean? What do I refer here by quantum chaos? So this is a picture that is supposed to show you a little bit what is my picture of quantum chaos. This landscape, when you have everything, you have some waves, you have some soliton-like stuff, you have particles and kind of black holes even. And to make it, let's say, precise, let's quote one of the founder fathers of our community of quantum chaos and semiclassical methods, Michael Berry. And he was insisting in that, well, we don't have exponential sensitivity to initial conditions in quantum mechanics. We all know the Schrödinger equation is linear. There is no anything like divergent trajectories there. There are no trajectories. So what you do when you link well-defined concept of classical chaos with quantum mechanics, he called it chaology, meaning you dig quantum mechanics looking for the manifestations of classical chaos. I don't love the name quantum chaology. I will talk about quantum chaos, but this brings us to the idea that there is a narrow sense to talk about quantum chaos, which are systems with a classical limit and a classical limit which is chaotic. And there is also an extended sense of quantum chaos, which is now has been hitting hard theoretical physics for the last 15 years, which is in a broader sense, meaning you look for the net of connections between properties of quantum systems, which were usually associated to chaos, like random matrix spectra, existence of Lyapunov exponent behavior in the out-of-stand order correlator, eigenstate thermalization hypothesis. There are these concepts that you can link to a classical chaotic background if you want, but if your systems either don't have a classical limit or the classical limit is very counterintuitive, these concepts are flying there. And the network of connections between them is what people refer nowadays as many-body quantum chaos. So if you go in the narrow sense, the way to address the questions of quantum chaos requires semiclassical methods. Why? You need a theory that links in a precise way quantum physics with classical physics. Beyond the intuition that the classical limit, the classical behavior is a limit. It's a limiting behavior of quantum mechanics. We need to make that precise. And in single particle systems or systems where the classical limit is the intuitive system of particles given by Hamilton's equations, which I indicate in this x-axis here. This is few particles but large actions. Typically, think about the Broglie wavelength, very small compared to the system size. This gives you a notion of this limit. And in this limit, then the classical limit is, I would roughly refer to this limit at h bar going to 0. And in this limit, the classical limit you obtain are systems of particles. And the regime where h bar is not 0, but asymptotically small, is called the semi-classical regime. You can also do it with several particles, and then what you get is that the classical limit of a system of a finite set of quantum particles when h bar goes to 0 is a finite set of classical particles following Hamilton's equations. However, there is an important realization is that you can talk about a different asymptotic limit where you can do semiclassics, which is the limit when you increase asymptotically the number of particles. In this regime, as you all know, the strict classical limit, the limit where the number of particles is strictly infinite, typically turns out to be a nonlinear field equation, like nonlinear waves, the Gross-Pitaevsky equation, Hartree-Fock. In this context, this is the classical limit. And the semi-classical regime is the regime where h bar takes whatever value it takes, but the number of particles is asymptotically large, but not infinite. In this regime, this regime is known, and this is the regime where I want to take you today, and we have been trying to reach during the last 6 years in Regensburg. So the main tool you use to do semi-classics, meaning to do quantum mechanics using classical information in the semi-classical limit, is the Gutzwiller propagator. So one of the questions I want to address is what is the corresponding object in the limit of large number of particles. And I want to stress that in the semi-classical regime, you do have quantum properties like entanglement, interference, and we want to address that. Semi-classics is not classics. Semi-classics is quantum mechanics with classical information. Now, what this limit is so fascinating for some of us is that living on this boundary you can get quite singular. So what I want to say by this precisely is the following. If you are probing a quantum system at a certain action scale S, for example, then you would think that the quantum behavior is the classical one plus corrections that are polynomial corrections that go to 0 when h bar goes to 0. And in the same way, in the other limit, going for large number of particles, quantum dynamics with a large, asymptotically large but finite number of particles is not, you would expect to be the same as classical plus 1 over n corrections. This is in many cases true, and this idea is very powerful. But you will be missing something that can be important sometimes, which is interference. Why is that? Because interference is about the existence of such terms. And these functions have an essential singularity when h bar is 0 or when n is infinity. So when you address this limit, you are dealing with singular objects. A quantum mechanical amplitude doesn't have a classical limit at all. A probability may have, but not an amplitude. So if you are dealing with amplitude, you have to deal with these kind of effects, which are non-perturbative, and they are the hallmark of quantum interference. So the machinery to deal with this, to capture quantum mechanical interference in the semi-classical limit is called the semi-classical approximation, or is what I call the semi-classical approximation. It starts with Mr. Feynman that tells you that give me an action functional. And then if you want to construct the quantum mechanical amplitude to go from some initial to some final configuration, you perform an integral over all possible histories, how to get from initial to final, classical and non-classical. Everything is in there. That's the beautiful integral representation of the propagator from Feynman. And to fix ideas, let's consider the one very basic question you address if you are able to calculate this object. If you know this object, you know everything about your system, but let's focus on this one. I want to know what is the probability to go from some initial configuration at initial time to some final configuration at final time. And the postulates of quantum mechanics tell you that this is the modulus square of the propagator. Okay, and so if you know the propagator, you know this probability, something that you can go and measure. The question that semiclassics pose is, where are the classical paths in this business? Where are they? Are they useful at all? In which regime they mean something for the construction of the propagator? And this question was addressed by many people at different levels of rigorous or physical intuition. It started with Mr. Van Vleck in the 30s. He derived an expression for the quantum mechanical propagator. He didn't start with path integrals. He started with WKB ansatz on the Schrödinger equation, but he derived that, following also ideas from Pauli and Dirac, that somehow the propagator should have something to do with the classical action. This is not the action functional, it's the action of the classical path. But he found that this object contained only one contribution, only one path, so it was valid only for very short times, had some problems, and it took one of the really big names in mathematical physics, I would say, Martin Gutzwiller, who started with the path integral and did asymptotic analysis when h bar goes to zero to derive this form of the propagator as a sum over classical contributions. So I will have one bit technical slide to introduce you to the semiclassical program in the sense of Gutzwiller. So we start with the path integral representation for the propagator. Before I continue, I would be very happy to be interrupted if anyone has any question. I prefer you to follow rather than to be quick. Okay, so we were in our crash course on semiclassics. Just start with the path integral. Now, you can make this idea rigorous, but let me be sloppy. I want to study this object when h bar goes to zero. So as you can perfectly see, and most of you know, this will be an extremely fast oscillatory object when h bar goes to zero. This means that in average, you will get nothing. The integral of a function that oscillates like crazy, you get nothing. So there are techniques and theorems in math that tell you which are the regions of your variable that contribute the most to such objects. You know them from statistical physics as Laplace method. You know them from complex analysis as saddle point approximation. In this framework, they are called stationary phase approximations because this is the version of the saddle point approximation when your function here is real. Therefore, the function you are integrating is oscillatory. It doesn't decay exponentially or grow exponentially, it oscillates. So now, the theory tells you that the places where this object contributes the most, in this language, the paths that contribute the most to this integral are the ones for which the action is stationary. And well, this is intuitive and it's very nice, and actually is Feynman argument how classical mechanics emerges from quantum mechanics. Not in the sense of the coherence and all that, I'm not talking about that, in the sense of where are the classical paths in my propagator? Well, if h bar goes to zero, they are the ones that contribute the most. Now, this is a path integral, I want to stress that. All these nice theorems about stationary phase approximation hold for finite dimensional integrals, but this is a different monster, and took Gutzwiller to be bold enough to apply these methods to this monster. But intuitively, this is clear. You get the classical limit are Hamilton's equations. This is Hamilton's principle. And super important is that you remember that the propagator has arguments, and the arguments in particular specify what should be the initial and the final configuration, or what in this example, what is the initial and the final position you are looking at the propagator. This means that your classical problem is a special classical problem, is a boundary type of classical problem. Why is this so important? Because in your lectures in mechanics, in my lectures in mechanics, I learn and I repeat like a mantra, Hamilton solutions have a unique solution. Hamilton equations have a unique solution. That's true. In which sense? In the sense that if I give you the initial position and the initial momentum, there is a unique classical trajectory emanating from this point into phase space. Now, if I give you a boundary problem, initial condition, initial position, and final position, then the solution is not unique if the problem is nonlinear, meaning it's unique only for the harmonic oscillator and in quadratic Hamiltonians. So in general, you have several solutions. Why is this so important? Because this is the way semiclassics deals with interference. In this monster, interference is hidden in this massive superposition, continuous superposition of oscillatory terms. Semiclassically, you will get a few of them. Can be infinite of them, but not a continuum infinite like in the path inter. So you have you can show that you have, except if you have focal points, something like that, but generically you have several solutions, and they are isolated. So what do? There is something that if you know a little bit about field theory, you are pretty much used to this, which is now I expand around the classical solution locally, and I integrate the fluctuations up to second order. This is called integrating the fluctuations. It's a Gaussian integral you can perform, and the result is what is called the Van Vleck-Gutzwiller propagator. So it expresses the exact propagator as a sum over classical solutions of the boundary problem in the given time. It contains the classical action of each path, contains a prefactor that knows about the classical stability of the path, and contains some topological index that talks about the classical flow around your solution. Now, this is the way classical information sneaks into quantum mechanics. I'm building an amplitude. This object, there is H bar there. This is a quantum mechanical object, but I constructed out of classical information. Now, in some other limit that we will see in a moment, further manipulations then produce the more intuitive idea of semiclassics as quantum mechanics following classical mechanics for a little time. But what I'm doing here is not that. This is an asymptotic analysis of the quantum mechanical propagator. How do we use this to describe interference? Well, I have now my propagator as a sum over classical paths. The phases you have here are given by classical actions, but an observable, think about the probability, think about an expectation value, think about the correlation function, typically involve K and K conjugate. So let's take the simplest case, an observable that contains two propagators, like an expectation value, or a probability, and then you have a double sum. How does it look? It looks like this. You have I just take the modulus square of this object. So you see the difference of actions here, and you have a double sum over paths. Every time you have a double sum over oscillatory objects that can compensate, you have interference. So the picture is that I have two paths now, going from initial to final. So one thing that should immediately jump to your mind is, well, the easiest way to get something that doesn't averages to zero, but you get something finite macroscopic out of this double sum, is to take the case where the actions are the same. And if the system is chaotic, you can show that this happens generically only when the trajectories are the same. So the first brutal thing we can do is, this is not only in chaotic systems. I mean, in general, only you have symmetries, the actions are different. So if you take that, let's see where does this lead. I make gamma 1 equals gamma 2. This is kind of the picture I have on the left. And of course, the actions go away, no H bar anymore. You have these omegas, which are just classical objects, and you can show formally that the object that you get from this diagonal approximation, when you take from the double sum only the diagonal part, the object that you get is the classical probability, or the classical transition probability, which has a very well-defined definition. Is I start with some initial configuration, I throw particles there with arbitrary momentum, and I look how many of them hit the final position, and I don't care about the momentum. So that's, of course, the classical interpretation of the subject, and you get it clean out of the formalism. This is something you can prove. Now, what is interference? Well, quantum effects must be in the rest. So inside this double sum, you have to go and scratch in the dirt if you want to look for combinations of trajectories that give you something that survives some macroscopic average or that you can observe. This super simple idea that many sums over classical trajectories have the classical limit plus fluctuation, quantum fluctuations that know about interference and are off diagonal, explains a lot. For example, the universality of random matrix type of spectral fluctuations in chaotic systems is explained with these formulas. Mesoscopic physics, you have weak localization, conductal fluctuations, lots of phenomena are explained with this picture. So it's a powerful picture. So I will give you a couple of examples of quantities you can address using these formulas. There are many, but I will focus on these two. One is coherent backscattering. This is a well-known wave effect. It consists that if you throw particles into a scattering region, because of quantum, and it's chaotic or there is disorder there, so eventually the momentum of the particles gets randomized. But if you look at it, you find out that there are more particles coming back to you than in average. This is called coherent backscattering, and it has been measured with cold atoms some years ago. What I have here is a bunch of non-interacting cold atoms. This is not Meribari physics. This is single particle physics. I bunched this cloud of cold atoms in some direction. Then I let the time pass by into a scattering region. And then you see that the momentum tends to get homogeneous. The energy is conserved, so the momentum gets homogeneous in the subject to the conservation of the energy. But if you wait long enough, you see this peak here. It's a substantial peak. It's 50% bigger than the rest. This is coherent backscattering, and it's a quantum interference effect that you cannot catch using Newton's equation or any classical approach that doesn't know about interference. The other observable I will refer later are the out-of-time order correlators. So these objects, I will provide more precise definitions in a moment, but roughly you can think about expectation values of squares of commutators between observables and time-evolved observables. You take the square means multiplying by that joint, because you want something positive defined that when you average doesn't disappear. So these were proposed already time ago by Larkin in the context of superconductivity, and they got a strong kick when Maldacena proposed this as a definition, as possible way to define the quantum Lyapunov exponent. And now is almost every paper in condensed matter refers to the calculation of the OTOC at some point. They are really useful, powerful, important objects in this business. So what I'm showing you here are results for single particle systems. This is a chaotic system called the Kicker rotor. It's very nice to use because it's numerically very friendly. Calculating OTOCs numerically is very hard. So that's why this system was the first system with very, very super clean numerical results for the out-of-time order correlator. And what you see is let me focus on the maximally chaotic regime, which is this black line. And you see an exponential increase up to certain time, and then a saturation. So there is a change of behavior here. The exponential behavior for short times is expected on the grounds on the very naive quantum classical correspondence that says that this object should look like the classical Poisson bracket square in some phase space average. So this is known. You can argue formally using Wigner-Moyal formulas, that for short times, this object should behave exponentially if the system is chaotic, with the Lyapunov exponent there upstairs. What happens after this time here is not classical. Classically, this curve should go on growing, but it stops. This is a quantum effect. The saturation is required because quantum mechanics is unitary, and unitary means coherence, and coherence is interference. So all these things should play a role to produce the saturation of the out-of-time order correlator. Now, what is this cute time where this change of behavior happens? This is called the Ehrenfest time in single particle systems. And it got different names. Now it's called a scrambling time in the context of black holes. And if you understand this from the point of view of quantum information, it's called a scrambling, breaking time. There are many names for that, but the notion is always the same. It's a time scale that marks the point where quantum interference is mandatory. You cannot go along with classical mechanics after, sorry about that, after this time. So a picture of the Ehrenfest time that you can grasp is a wave packet in a chaotic billiard. You start with the wave packet, localize something, let it go, and eventually it covers the whole billiard region, the whole billiard domain. So of course, you can already imagine that I can do my quasi-classics here. I can use the motion of the center of the wave packet as moving along classical trajectories. At the very beginning, then probably when you hit once the wall, maybe, but already when you hit more times, this won't work. And when you are here, this won't work at all. So at some point, the classical picture of the wave packet following classical trajectory simply breaks down, and breaks down because of interference. So how to estimate that? We typically, what we do is to consider a wave packet which is very small, quantum size, small, and ask what is the time after which the chaotic classical dynamics forces this thing to spread over the whole space. And what you get is that the Ehrenfest time is inversely proportional to the Lyapunov exponent that produces this divergence, and proportional to the log of the H bar. That's very important. It's a short time scale. It's not algebraic in H bar, it's logarithmic in H bar. The Ehrenfest time is a very important object in mesoscopic physics. I won't go into that. So let me summarize what we have so far. So far, we formalized this intuition that we all have from the two-slit experiment. When you think about the two-slit experiment, you think about one trajectory going there, one trajectory going there, and then interfering. So what you are doing there is adding contributions from different classical trajectories that interfere. Now, what Gutzwiller did for us was to formalize this and completely generalize this picture to any system in the semi-classical regime. We showed that the interference comes from correlated actions. You want interference effects to survive, you need action differences to be small. Otherwise, they will be completely washed out. And these effects kick very quick in chaotic systems. In integrable systems, the break-it time is algebraic in H bar, but now it's logarithmic. So this happens fast in chaotic systems. So you need to consider this if you are looking at not ultra short time scales in the dynamics of quantum systems. You need to consider interference, especially if they are chaotic. So now we want to lift all these things, and we want interactions, we want indistinguishability, we want quantum fields. This is the ultimate goal. We want the most powerful description of many-body systems is quantum fields. We want to do semiclassics in quantum chaos for quantum fields. It would be good because so far the effects I show you, like coherent backscattering, is a wave effect. It's there because the Schrödinger equation is a wave equation that therefore admits superposition in a space. But if we move this to the space of many-body systems, then we are dealing now not to waves, but really with something that is inherently quantum chaos. And that's kind of one of the leitmotif of the research in this area. So if you're a field theorist, I apologize because my colleagues in field theory tell me that to call the Bose-Howard model a field theory is like, give me a break. So, but okay, this is our first field theory we are going to address. There are bosons in the lattice. So you have on-site energies, they can jump around, they can interact with each other. The typical Hamiltonian has something that moves the bosons around and something that represents the interaction. This is called the Bose-Howard model. And the Hilbert space of this system is spanned by what is called Fock states, which simply tells you how many particles you have in each of these wells. If you want, you can, there are other pictures. This is just a picture, there are others, but you simply specify how do you populate, how many particles are in certain single particle states, and this is what it's called a Fock state. And linear superpositions of Fock states build the Hilbert space of many body systems in general, not only for bosons. For bosons, these occupations can be whatever. For fermions, only 0 and 1. That's the point. Now, if I want to do semiclassics there, and I want to define chaos and do quantum chaos in the narrow sense, I need a semiclassical theory, and the starting point is a semiclassical approach for the propagator in Fock space, meaning the transition amplitude between some initial configuration to the final configuration in time t under this monster Hamiltonian. And what we are going to do is, you can show, I didn't do it, but you can show that actually the role of H bar will be played by the inverse total number of particles. This can be shown. So the semiclassical approximation is a good approximation when the occupations are large. Not only, typically it happens what happens with asymptotic approximations. They work extremely good even in regimes that you wouldn't expect. But in principle, the conservative point of view is large occupations. So we want an expression for this propagator when the occupations are large. Okay, guess what? It took 3 years and a lot of suffering from Thomas Engel, but he derived the semiclassical propagator in Fock space, and it looks like the Van Vleck-Gutzwiller propagator. The H bar you have here is actually the inverse number of particles. So this is a non-perturbative object in the number of particles. It oscillates infinitely fast when the number of particles goes larger and larger. And the important thing is, okay, then what is the classical limit? The classical limit is built. Remember that this propagator links some initial configuration, certain number of particles at each single particle state, with some final one. That's this information must be there. Now, what do I call the classical paths doing the job? Well, the classical paths are solutions of nonlinear mean field equations. In this case of the Bose-Howard system, there are solutions of the discrete nonlinear mean field Gross-Pitayevsky equation, which is this one. It's just the lattice version of Gross-Pitayevsky. And you have to go find all the trajectories, meaning the time-dependent complex fields, vector fields from psi 1, psi 2, psi 3, up to the number of sites. You have to solve this monster under the boundary conditions that the moduli of these fields hit the occupations. This is kind of, if you have done bosons, this is kind of obvious. I mean, you interpret the modulus square of any bosonic mean field object as some occupation, some density. So this is doing that. So why do you have several solutions? Well, because these conditions are fixing the occupations, meaning the modulo of the field, not the phase. This plays the role of momentum. So I have to solve this boundary problem, find the correct phases to go from this configuration to that configuration in the time. And I'm not saying that this is easy, okay? That's a substantial work you have in there. But the picture, we can really extrapolate from what we know. Whatever this thing is, whatever the Gross-Pitayevsky equations are, they are Hamiltonian. There is a Hamiltonian. So I can talk about chaos perfectly. It's perfectly well-defined concept here. Classical mean field chaos is perfectly well-defined. And then I can pose my question, which are the quantum signatures of this mean field classical chaos? Where is interference there? Yeah, because I have several mean field solutions that now produce interference through oscillatory terms with the actions. So this program, we push this program, and from the rest of the talk, I will show you the application of this object, of this thinking in Fock space, to some systems. So first, we will talk about OTOCs, then kind of echoes, meaning autocorrelation functions, and coherent backscattering in Fock space. And if I have time, we do many-body spin echo, all with this machinery. Okay, so let's, as a warm-up, let's take an easy one, coherent backscattering. We should know what to do in there. The probability to go from some initial to some final configuration in Fock space is a double sum over mean field solutions. No? We do our business. Now these initial and final points of my dynamics are given by Fock states, sets of occupations, not positions, occupations. And we need to look for action correlations. So the first thing that if you work on it, you will realize is that if the initial and final configuration are different, then under a little bit of average, this thing collapses pretty quick into the diagonal approximation and gives you the classical probability. What is the classical probability here? If you know about bosons, you know what I'm talking about here. This is what we call the truncated Wigner approximation. Classical mean field propagation of quantum mechanical wave packets. So that's here. And this works very well if the initial and final point are different. Now, if they are the same, well, again, you have the possibility that the two trajectories are the same, diagonal approximation, but something cute happens now. You also have the possibility to go, since initial and final are the same, you can go like that or like that. These are two different trajectories. So this is interference, but they have the same action if the system has time reversal symmetry. So because of that, you get an enhancement of a factor of 2. You can show that it's a factor of 2. This is now in Fock space. This is not a particle going here and there. This is the whole configuration moving in space-time and giving you a different probability to come back to the same or to another one. And for this, you need chaos. For this, to obtain the factor of 2 there, you need chaos. So our prediction is that if the Gross-Pitagetsky equation has time reversal invariance, that is expressed by this, and you have a mean field chaos that you can check, then we have an enhancement of the probability of return. This we checked against quite heavy numerics in the Bose-Hobart ring, which is presented here. I'm throwing an initial state, which is this one, 3 particles inside 1, 3 particles inside 2, 2 inside 3, and so on. And I'm calculating numerically the probability to get them somewhere else in another configuration. And you see that they are pretty much flat, and they follow the truncated Wigner approximation, these crosses, except when you come back to the same state, and then you have this enhancement. What is the typical signature of coherent backscattering is that is destroyed by time reversal if you destroy time reversal symmetry. This is the first thing a mesoscopic guy will tell you. If this is coherent backscattering, you should kill it with killing time reversal. So we introduce kind of gauge field, which is this phi here, to make the job, and we show that effectively the coherent backscattering peak goes down if you break time reversal symmetry. The remarkable thing for us was that although this is an asymptotic theory for large occupations, turns out to work, the effect survives and is there, even with quite diluted systems. So this should give you a hint that somehow things with fermions may work, and they will. I will show you. Okay, this has warm up. 2 trajectories, we know our business. Let's do OTOCs. That's more difficult, much more challenging. I will introduce quadrature operators just because they are quite useful. They look like the standard positional momentum, but this is not positional momentum or anything. This is a field. You don't have positional momentum there. It's something else. But they are Hermitian with continuous spectrum, so they look like positioning momentum in a single particle quantum mechanics. And we choose as a OTOC one that contains momentum and position in the certain site. Okay, now the monster is substantially bigger, because if you see the OTOC, it has 4 time evolution operators. That's why it's called OTOC, by the way, because it has this structure. And then the semiclassical approximation demands you to use 4 propagators around. So you have a sum over 4 trajectories, and you have to play the game of looking for interference there in a much larger space. But this can be done. This is schematically what I mean by the 4 trajectories. You integrate over everything here, but a couple of trajectories, they join at certain positions, and 2 of the positions you are integrated are kind of tight because you put a wave packet there. This is, I don't want to go into detail, but this is just to understand the pictures I'm going to show. So we need to look for combinations, constellations of trajectories that either have 0 action difference or small. to see something different from 0 in this object. So the first thing you can think is, okay, let's put all the trajectory very close. Then the action should be it's kind of generalized diagonal approximation. You can show that they will produce the leading order, the classical contribution to the OTOC. What happened, diagrammatically is something like that. They are very close to each other. Now, the contribution to this configuration after a long calculation, I want this long technical, is that this produced the expected exponential behavior of the OTOC 4 times shorter than the Ehrenfest time. Great. Why do you have an Ehrenfest time there? Because if you want to squeeze these guys, you have to make an effort to squeeze them because the dynamics is hyperbolic. They want to do that. And therefore, this approximation cannot hold on if the time is too large. And now we know then that before the Ehrenfest time, we have the exponential behavior. Great. And we know what is the Lyapunov exponent. It's the classical Lyapunov exponent of the mean field dynamics that can be calculated because in mean field you have fields that separate exponentially because the equation is nonlinear. Everything nice. Now to go beyond the Ehrenfest time, you have the machinery of action correlations tells you look for configurations where the trajectories are very similar to each other pairwise, but except in a region that is called an encounter. I won't go into the heavy details of this. This is quite a heavy machinery, but you can go count these encounters, apply ergodic arguments, do some average. It's a long way. And what you obtain is the sets of configurations, the constellations of orbits for which this action difference is small, and therefore they survive some average, meaning the integral over the Wigner function representing the initial state, this kind of average. And what you can show is what you should expect is that this behavior for the out of time of the correlator. For short times exponential behavior and then saturation. These diagrams give you the mean field, the exponential behavior. These diagrams give you the saturation. So this is a quantum interference effect that knows about unitarity and takes care of the correct long time behavior of the OTOC. So this is satisfactory to get, certainly, and it worked. So now I challenge you to tell me what is this. This is an OTOC, also another system, but I'm showing you the result. As you can see, I'm changing here the number of particles. So take the largest number of particles, the darkest blue curve, last one here. You see, this is a detail of the short time. You see exponential behavior, no doubt about it. But no really a saturation. Things oscillate. And they oscillate with a period that has nothing to do with the recurrence time. The recurrence time is astronomical here, nothing to do with that. Actually, the period is logarithmic in the number of particles. So you have this initial growth, but oscillations. So guess what is this? This is a critical system. It's an integrable system with a critical point. Then because it's critical, it's hyperbolic, you have initial exponential behavior, and because it's integrable after all, you have this oscillation. Okay, now I have only 2 minutes, so let me tell you about the another observable, and I want to tell you now, so far you can tell me, hey, but you are using averages, you got these universal results. Can you make this machinery work in detail? The answer is yes. So I will show you what is called the autocorrelation function for a Bose-Howard system. These calculations are challenging because you have to understand the classical dynamics in a high-dimensional space. This can be hard, but our colleague in Washington is really a master on that. I will only show you the results. This is a 4-side Bose-Howard model, and I'm looking at the survival probability for a coherent state, which is given by these complex labels. Doesn't matter, we are in a regime where it's not that chaotic. And what you see here are the blue curve are numerical exact calculations. The red is the semiclassical approximation, meaning we constructed all the paths, all the actions, all the indexes, put all together, and this is what you get. The dotted line is the truncated Wigner approximation for the system. And then you see that the truncated Wigner, the classical, works for a short time, but then it doesn't capture, it captures the mean behavior, but it doesn't capture all these wiggles which are interference. While the semiclassics, okay, semiclassics get it very, very, very nice for very long time scales, well beyond the Ehrenfest time. So you may ask, okay, but who cares about all these wiggles? So let's take an average. For me, it looks also convincing that truncated Wigner catching just the average behavior is good enough. Why not? Well, this doesn't work always. This is an example of a calculation in a similar system. Green is truncated Wigner, blue is numerics, and there you see the difference between truncated Wigner and numerics. Why is that? Because there is robust interference here due to symmetries, and truncated Wigner doesn't know about that, miss it completely. We have a theory to extend the truncated Wigner minimally to include robust interference effects, and is the red line you see here. So it works. Okay. I will just show you a picture because I'm very proud of this picture. This is a picture of many-body spin echo. No, probably not. I think someone is interested, you can ask me, but I reached my time. What I want to convey here is that okay, what is important about fermions? I won't show anything, but what is important about the many-body spin echo is that these are fermions. And there is the usual understanding that fermionic systems don't have a classical limit. And I don't agree with that. I think they do have a classical limit because you can construct a path integral. And in my, the way I see things, if you have a path integral, you can define a classical limit. Now, the question is whether you have a semiclassical regime. And this, I agree, for fermions is super delicate, but we apply the semiclassical machinery to fermionic systems. Things get super complicated. The classical limit is super ugly, but you can do it. And we get really, really good results there. So it's not clear why, but actually it seems to work, and this is work in progress. So there is much to explore in this regime. There's much to be done. Is lots of interesting effects that we should try to address. I have just a brief list. I mean, there is the Berry's random wave model, how to take it into Fock space, how to understand Maldacena as bound, how to do fermions, understanding what we are doing, how to construct the Gutzwiller trade formula and Berry tower for the system, boson sampling, and more. And with this, I thank you for your attention and looking forward for your comments.
Thank you, Juan Diego. That was great. Very beautiful talk. So, while we wait for people to pose their questions, as I was saying, there's always a little bit of delay. I'm going to take advantage of my position. I'm going to start with a question of my own. I have a few, but just at the end, well, I'm curious about the movie, but I just want to make a question about just a few slides before, when you were comparing what you got with the truncated Wigner and the full numerics, this one. So that, yeah. So, I recognize that reference that Nature Physics is, one of the typical quantum simulation or famous quantum simulation papers in which you have kind of this huge simulation of the Bose-Haber model, and they show that they reach regimes in which their numerics kind of start failing. And so I was curious here, you have these three things, right? You have the blue curve in this approach, you have the red is the numerics, I guess, and then you have the truncated Wigner. This is out of ignorance. I'm curious about how the numerical cost of each of these approaches compared to each other. Can you comment about that?
Yeah, doing semiclassics by the book is heavy. It's one has to, I tell you why first, is because you have to solve this shooting problem. So it's very easy one of the beautiful things about truncated Wigner is that it's kind of initial value representation. You start with positional momentum and let things evolve. In the semi-classics I present here, you specify where do you start and where do you want to get. And this is a different kind of monster, and is pretty heavy. On top of that, for this particular case, when you propagate coherent states, turns out, for some technical reasons, you have to complexify the classical dynamics. So you have to take the discrete Gross-Pitarski, complexify it. It's already a complex field. By complexify it, I mean that take the real and imaginary part as independent complex variables and solve the boundary problem. So this is awfully, it scales awfully with dimension, with the number of sites. And we are not going to beat matrix product states or something like that doing that. That's for sure. Now, that said, the idea, this was a proof of principle, this calculation. That if you do things by the book, they work. Now, this calculation, the classical calculation we did here scales exactly as truncated Wigner. So, and this is because here we don't need to calculate every path, every action. We only need to be clever in finding out which paths have correlated actions, and then I forget about the actions. And you see the results are really, really work perfectly well. So the idea we have in mind is to use semi-classical thinking to improve the very good scaling of truncated Wigner, which is really amazing. Truncated Wigner is fantastic. That's out of the question. And this is the philosophy of the approach we have right now. Let's say.
That's great. Thank you. All right. So moving on to the comments. So we have a bravo in the comments from someone that I think is Carlos Pineda, which you might know. And then Manuel is asking, he's asking a question. Manuel Munoz, he's asking, can you comment about how to approach boson sampling with your method?
Wow. Hey, thanks, Manuel. I love that. Yeah. So there are two instances. I don't have this slide here, Pity. There are two instances to do boson sampling with these methods. One is, I think I have to remember people, boson sampling is scattering of complex scattering of non-interacting bosons. So I inject a Fock state here. There is a scattering region, and I see what goes out. It sounds trivial, but it's absolutely non-trivial because the mathematical object that you get, they are non-interacting, but the mathematical quantity that you get in order to evaluate transition scattering amplitudes and probabilities in this many bosonic case is not a determinant, it's a permanent. And permanents are terrible. If you want to calculate a determinant, well, you diagonalize your matrix and you know how to do that. A permanent is something completely different. And a permanent built from the elements of the scattering matrix, which are complex, is even worse. So you have a supermassive sign problem. And then it's so bad and it scales so badly in a classical machine that is one of the, as you may know, is one of the candidates to show quantum supremacy. I don't know the state of the art there, but it's one of the, at least 2 years ago, was one of the candidates. And people work hard on this. Okay, that's it. You can approach this in two ways. You can consider each of the bosons as a particle and treat this as a single particle problem with lots of combinatorics, and do the action correlation machinery plus the combinatorics of bosons. And this is what we did in the paper. One of the papers we have in boson sampling is chaotic single particle scattering plus combinatorics. Now, the other way, which I consider deepest, deeper, and more fundamental is the following. Bear with me. Remember your complex field. Sorry, I want to show this. Where was it? Here. These are your complex fields that are kind of the classical representation of your bosonic fields. There is no surprise there. Now, when you pose the scattering problem, injecting a Fock state and asking what is the probability to get another Fock state out, you are fixing again the modulus of the complex fields in this classical picture. Now, this problem of some scattering in the middle and some connecting the modulus of the incoming and outgoing waves is a classical problem in optics. It's called the phase retrieval problem. It's like Fourier analysis. Imagine that I tell you, hey, I have these two Fourier, I have this series, this time series, and the Fourier version of it in real space and in Fourier space. And now I give you the modulus square of the signals, but not the phases. Give me the phases. That this is called a phase retrieval problem. Should sound familiar. This is what we were doing here. I give you occupations, give me the phases. So this is a nonlinear phase retrieval problem. Terrible. But without interactions, without this, it's still terrible because the solution is so multi-valued that if you impose this boundary condition, you get lots, can be even exponentially large number of solutions. And this is the origin of complexity from the semiclassical point of view, is the origin of complexity in boson sampling. And right now what we are doing is trying to relate the complexity of boson sampling with the fractal structure that you get when you solve this phase retrieval problem, which is a root search problem, which is very hard. And so these are the two pictures of boson sampling in our using this machinery. Thanks.
All right. Thank you for the answer. Let's check if we have any other questions. All right, I think that's it. And it's just in time, it's 10 o'clock. So thank you, Juan Diego, once again for this fantastic talk. And thank you everyone who was on the other side listening. I'll just announce that, of course, next week we have a new seminar, which is going to be given by Ana Maria Rey from Gila and Colorado University. She'll be talking about entanglement dynamics and scrambling in a trapped ion quantum magnet. And so we hope to see you all there. And that's it for today. Thank you. See you next week.
Thank you, everyone. Thank you.